So welcome back. We continue with our lecture on electrochemistry, and this week I'm gonna complete that chapter. So today we're gonna look at the different groupings or branches of electrochemistry. It's a very vast field. In actual fact, this is a field that you can possibly do in a couple of years. There are monographs, that are written about electroanalytical chemistry. And so we're just gonna cover in very brief scope, of what it is, so that everyone can have just a bird's eye view about electroanalytical chemistry. So electroanalytical chemistry is grouped into two groups. There's what you call the Faradaic methods, and there's what you refer to as the non-Faradaic methods. So the Faradaic method just means, that reduction and oxidation is happening. So there is current, that is being transferred from the anode, where oxidation happens, to the cathode, where reduction happens. So, reduction and oxidation is happening. Now, in non-Faradaic methods, on the other hand, even though you are measuring the current and the voltage, now there's no reduction or oxidation, that is taking place, all right? Even though there is potential difference involved, and I'm gonna discuss how that potential difference is obtained, there is no, so there is no redox process, okay? Yeah, so in this case, there's a redox process, whereas in this case, the non-Faradaic, there is no redox process, and as such, you do not have electrons, being transferred. Now, the Faradaic methods, are equally categorized into potentiometry. And potentiometry essentially means this is where you are measuring voltage. So the signal is voltage. Faradaic methods can also be categorized into voltammetry, and this is a very vast field. We talk a lot about it in Chem 311. With voltammetry, you're measuring current, okay? So you're measuring current, and you're measuring current at variable potential, at variable potential. And this is important, because every analyte has got a very specific potential at which it can get oxidized or reduced. So with voltammetry, what you're doing is you're sweeping or changing the potential until the point at which that analyte gets oxidized or reduced, and then you measure the current, okay? With coulometry, on the other hand, which is a branch of Faradaic methods, you're measuring charge, okay? You're measuring charge of the electrochemical device. And lastly, with amperometry, it's very similar to voltammetry because you're measuring current, okay? But you're measuring current at fixed potential. You're measuring current at fixed potential. So those are the groupings of Faradaic methods. And in this course, my focus is only gonna be on potentiometry, which sometimes we call it the classical, method because you're measuring, the voltage, and it's essentially a galvanic cell. So it's a very mature field. It's a galvanic cell, okay? On the non-Faradaic methods, on the other hand, where there's no redox process that is taking place, you can group them into potentiometry again. So again, in this case, the potential difference is generated out of a charge separation where you've got two sets of membranes, separating two ions. And because of that, you've got, a charge separation giving you a potential difference, and potential difference actually means a voltage. Sometimes we call these the non-classical potentiometry, And is the most common nowadays, especially when you're trying to make different types of sensors, or what you call the ion selective electrodes. So if you take a pH electrode, for example, is a classical example of a non-classical, potentiometry, because the charge separation results to the voltage that you read. Now, another method for the non-Faradaic method is what you call conductimetry. In this case, you're just measuring, conductivity. Okay. Maybe you can take a look at this paper if you're interested, because there has been a lot of misconceptions, trying to differentiate between the classical potentiometry, which is a galvanic cell, and the non-classical, potentiometry, which is the ion selective electrodes, because of the usage of terms, they are used interchangeably. And even the theory, has been, the theory for the non-classical potentiometry has been borrowed, from the classical potentiometry, and sometimes, it is not very accurate. And so based on Chang's paper, you're gonna see some of those inaccuracies. So as I said, my focus is only gonna be on potentiometric sensors, and I won't talk about, these other types of, electroanalytical techniques, which you're gonna cover in higher level courses. But you should know that, there are many applications, of potentiometric sensors, and some of you doing your research projects or your term papers on this field, you've already seen the very wide scope, of the applications of potentiometric sensors, or what I'm calling here ion selective electrodes, which are the non-classical potentiometry. So of course it can be used for many applications, such as pharmaceutical monitoring, pollution control, things like agriculture, medical devices. It's a very common type of technique. If you take a look at, this table that I got from the textbook, you're gonna see you can analyze different types of ions using potentiometric sensors. You can analyze biochemical analytes such as lactates, glucose, and so on using potentiometric sensors. Things like urea and so on. Very important kinds of analytes in medical diagnostics. And as such, potentiometric sensors is very relevant and important. So as I've said before, with classical potentiometry, the basis is just simply, galvanic cell. And as you well know, galvanic cell, is spontaneous. The electrons are being transferred, from the anode, to the cathode. On the other hand, if you reverse the order of the anode to the cathode, for example, in this case, now you call that an electrolytic cell, and you guys did this in Chem 102. And the only difference is, in galvanic cell, the redox reaction is spontaneous. And, with the electrolytic cell, the redox process is non-spontaneous. And what really that means is that in this case, you need energy to drive that reaction. And so the energy, often is given, by a battery. So you need a battery in this case. Sometimes people call it a potentiostat. You need a battery that pushes, the voltage so that you can drive, the redox reaction, that is non-spontaneous. That one is called electrolytic cell, and is a basis, of voltammetry and amperometry, for example. So hopefully that's clear. So quick summary on potentiometric sensors. As I have said, in this case, we measure voltage, that provide the chemical information that you're trying to explore. Now, one huge advantage of potentiometric sensors is that it's very miniaturizable. So these things you're calling ion selective electrodes, the non-classical potentiometry, you can make it very small. And that means you're able to do analysis in situ. So meaning if at all I wanted to say analyze say dopamine in a rat's brain, I am able to make a very small electrode, a nano electrode, and just poke, into the brain, into the rat's head, and actually do in situ, analysis, which is very, very important. Also, you can do wearable devices. One a huge application of potentiometry is the fact that you can make it into wearable sensors, which is the basis, of your term papers anyway. So take note of this, that for potentiometry, particularly the classical potentiometry, you want the analyte to be electroactive. And what electroactive means is that analyte is prone to undergo oxidation or reduction. So that's one requirement of classical potentiometry. However, when you're doing the non-classical potentiometry, the ion selective electrodes, essentially any type of analyte, you can actually fabricate an ion selective electrode for it. Okay. Now, in terms of components, the components of potentiometry consist of largely two electrode system. Because like I said, the configuration is largely borrowed, from the galvanic cell in either classical or non-classical potentiometry. So essentially you've got the cathode, which is the sensor or the indicator electrode, sometimes you call it. And then you've got, on the left-hand side, you have the reference electrode. And last week, I talked about the 3 different types of reference electrodes that are commonly used, although the silver chloride, is the most common type of reference electrode. And the reference electrode means, the potential is known as a constant potential. So the E of the cell, that you actually measure, the E of the sensor, the voltage of the sensor, which is what you measure, is actually generated, by taking the potential of the indicator electrode, which is the cathode, minus the potential of the left-hand side, which is the reference electrode, which is at fixed potential, and it's known, and that gives you the E of the cell. So take note of this, irrespective of what a reference electrode you use, if you know the result of the E of that cell, you can interconvert, between different types of reference electrodes. I'll give you an example. Assume you have a situation where an indicator electrode, has a potential of this against a saturated calomel electrode, which was, this mercury reference electrode. And we know that the mercury reference electrode, has got a potential of 0.241 V. So essentially, if you're asked to calculate the E of the cell with respect to the standard hydrogen electrode, you can just simply do a very simple relationship. We already know the E of the cell is equals to the E indicator minus the E reference, and so I just substitute as such. And so I can determine what is the E indicator when you're using the saturated calomel electrode. And of course you can get that. And then I can determine the E of the cell with respect to the saturated calomel electrode just by substituting this up here minus the fixed potential of the reference electrode for the saturated calomel electrode, which is that. And if at all I wanted to check the E of the cell with respect to the silver chloride, I just need to substitute this, to the fixed potential of the silver chloride. And so the E of the cell in that case is going to be that. So again, very, very simple, of course, interconversion. Now, one challenge with potentiometry, just like all other instrumental methods, is that we know every instrumental method, has got an error, has got an instrumental error, okay? Now, the instrumental error that is pertinent to potentiometry results from what you refer to as the junction potential. If you remember how the galvanic cell works, it's that, and of course you can refer to the slide, slide 1 or 2, is that you've got the outer circuit. You've got the outer circuit, so you've got the reference electrode here, you've got the indicator electrode, and then you've got the outer circuit where the electrons are flowing, and then you've got, the inner circuit, and the inner circuit is what you refer to as a sort bridge, if you remember. So the junction potential results, from the potential that is generated, from the sort bridge. So how is that potential generated? Remember, the sort bridge helps in the conduction of the ions from one cell, from one half cell to the other. And with that conduction, you've got these ions, and every ion has got a certain weight. But each ion also has got a certain charge. And because of that, ions have got different mobilities. Ions have got different electrophoretic mobilities, as you can see, in this table. And as such, you get into a situations where some ions move faster than others, and because of that, they create what you call a charge barrier, which is a charge separation. That's what a charge separation is. For example, in the case of sodium chloride, in water, we know that it's going to dissociate into the sodium ions and the chloride ions. And of course, we know this is an electrolyte. Now, the chloride ions, if you look at the electrophoretic mobility, the chloride ions move faster, than, the sodium ions. And so because of that, they are lighter, and so they accelerate faster, resulting in what you call the charge separation. And this charge separation is what you refer to as the junction potential. Remember, that junction potential is an error. And that's why you find if you take a pH electrode or any other potentiometric sensor, it's always, jumping around, because of that junction potential, because of this mobility, of the ions, that cause a charge separation. So please take note of that, a very common error in potentiometry. So what's the solution? So we don't have a very good solution. It's always there. The junction potential error is always there. However, you can minimize it, by choosing the right type of electrolyte, which has got, constituent ions that have got very similar mobilities. And that is why you find in most potentiometric or even voltammetric techniques, potassium chloride is the most common electrolyte out there, because the ion mobilities, of the ions are very, very similar, and so they minimize, the junction potential. So there are different types of indicator electrodes that you can fashion into a potentiometric sensor. Now, you can use the metal electrodes. They're the most common, the metal electrodes. So things like platinum, things like gold, things like cadmium, things like mercury, all these metals sometimes are used as indicator electrodes. That is very common, when you're doing classical potentiometry using the galvanic cell. Remember that, using the galvanic cell. Now, but when you're using the non-classical potentiometry, often we use these other type of electrode system called ion selective electrodes. Ion selective electrodes. And by the way, maybe I backtrack a little bit. So for the metal electrodes or the solid electrodes, other than the metals, you can also use carbon. Carbon is also another very common, type of electrode that is used, when you're making potentiometry. And the reason carbon is very good, it's because, one, it's very inexpensive, but also it has a very big surface area depending on the type of allotrope of carbon that you're using. There are many allotropes out there. Of course, of graphite is very, very common. But recently, people have been using carbon nanotubes, which is a tube morphology, of a graphite. And also very, very recently, maybe in the last only 5 years, graphene is another type of allotrope of carbon that has just been discovered, which is essentially a two-dimensional graphite sheet. Remember, graphite is a three-dimensional, graphene is a two-dimensional carbon allotrope. Very, very conductive. I use it a lot, in our research lab here. So also do we use a lot of carbon nanotubes as well. So remember, those types of electrodes are used a lot when you are making potentiometric sensors. So let me now talk a bit about ion selective electrodes, which, as I said, is the most common type of sensors, that are used in potentiometric devices. So the ion selective electrodes, generally respond selectively to an ion. Remember, this is non-classical. And so they do not involve a redox process. So unlike metal electrodes, in this case, with ion selective electrodes, there is no redox process. And so the charge is generated, from a charge separation resulting from a very thin membrane. Okay? And so this is how typically it works, where you've got a membrane and the membrane separates the sample, from an inner solution, and the inner solution has got a known concentration. So maybe this can be glass in the case of pH, and inside you've got a known concentration, say, of HCl, and then outside you've got a sample where you do not know the concentration. And so because glass is going to be selective to hydronium ion, the hydronium ions get captured on the glass membrane. And because of that, there will be a charge barrier, because there will be ions trapped here and there will be ions in solution. They create, a charge separation. And anytime you get a charge separation, a voltage is generated. And so that is the basis, of ion selective electrodes, where you make a membrane that is selective to the analyte of interest. And so this one is called, the non-Faradaic process. And so the E of the cell then, actually gives you, this kind of relationship, which is called the Nast equation, where the constant here, refers to, the mobility of the ions between the glass membrane or the membrane and the sample. And, this one is a typical constant, in the Nast relationship, all right? And you've got the logarithm of the analyte of interest. So this is a Nast equation, which characterizes, what you refer to as potentiometric devices, or both classical and non-classical as well. And maybe I should emphasize, that potentiometry, really doesn't detect, concentration, but instead they detect, activities. Okay, remember that. Potentiometry detects the activity of the analyte. The good thing is the activity of the analyte is proportional to the concentration, multiplied, by the activity coefficient. Now, in most cases, activity coefficients, are very, very close to 1. And so that is why we make this approximation, that the E of the cell is proportional, to the concentration. But ideally, we are measuring activity in potentiometry. Now, one important figure of merit, when you're doing ion selective electrode is what you call selectivity coefficient. Because remember, with ion selective electrodes, you're trying to detect only one analyte, okay? So the device is selective to only one analyte. And so if at all I've got a very complex mixture, my sensor is only responsive to only one analyte. And the way you try to determine the performance of a sensor is using this figure of Mary that we talked about earlier on, called selectivity coefficient. And the selectivity coefficient, is determined by the response, to the analyte, and the response, to the matrix, and so that's how you get, the selectivity coefficient. Of course, ideally, we want the selectivity coefficient to be very, very close to zero, meaning the analyte is very, very responsive, to the device is very, very responsive to the analyte and not to the matrix. So X here is the matrix, okay? But it's a matrix. But the point is, it's almost impossible to make a sensor that's completely or 100%, selective to the analyte. So in some cases, there's always a little bit of interference. And so that's why in the Nast equation, often ideally we would represent it as such. The E of the cell is equals to the constant, related to electrophoretic, mobilities of the ions taking place. And then you've got that constant, N is the number of electrons, that is being transferred. In the case, of course, of classical potentiometry, this is the activity of the analyte, you can see, which is often very close to the concentration anyway, because the activity coefficient is very close to 1, plus, this selectivity, coefficient. You can see that the selectivity coefficient of A relative to X multiplied by the concentration or the activity of A, and so on. And so that is the E of the cell. So in the next lecture, I'm gonna give you very specific examples of ion selective electrodes. And as I said, different chemistries that you use to make these membranes that you can integrate, to make the ion selective electrodes or the non-classical potentiometric sensors. So we're gonna continue on that next time.